Imagine this, you are standing near a bridge, thousands of vehicles cross it every day. Cars, trucks, buses, people now suddenly. An engineer asks a terrifying question. What happens if this bridge faces an earthquake? There are only two ways to find out. First, wait for a real earthquake. Obviously, that is dangerous, expensive, and stupid. Second, recreate the bridge inside a computer and simulate the earthquake. And that is the power of computer simulation. Today, we are going to explore something extraordinary. How do computers simulate reality? How can a machine predict the behavior of atoms, chemicals, buildings, and even living organisms? And more importantly, can we simulate the universe itself? By the end of this video, you will understand what computer simulation is, what models are, the different types of models and simulations, how simulation actually works, and how we simulate natural systems. Let's begin. We live inside a universe full of complex systems. Weather changes every second, chemical reactions happen invisibly, cells divide, stars collapse, markets rise and crash. Reality is messy. If we want to understand these systems, we usually do experiments. But experiments have problems. Sometimes they are expensive, sometimes they are dangerous, and sometimes they are impossible. You cannot physically experiment with a galaxy. You cannot directly observe every electron in a semiconductor. You cannot repeatedly crash airplanes to test safety, so humans needed another method, a way to experiment without touching reality. That desire gave birth to simulation. Computer simulation is the process of recreating a real world system inside a computer using mathematical rules, then observing how that system behaves over time. In simple words, we study reality, we convert its rules into mathematics, then we let computers execute those rules. The result, a digital version of reality. That digital world behaves according to the rules we gave it. This allows us to analyze behavior, predict outcomes, and solve complex problems. Think of simulation as a laboratory inside a computer. Instead of physically experimenting in the real world, we experiment in silicon. But here comes the big problem: computers do not understand bridges, they do not understand atoms, they do not understand rain. A computer only understands numbers, zeros, and ones. So, how do we make a computer understand reality? We need something called a model. A model is a simplified representation of reality, not reality itself. Just a structured approximation, a model captures the important behavior of system while ignoring unnecessary details. Let's understand the major types of models. The first is a physical model. This is the most intuitive model. A physical model is a tangible representation of something. Imagine building a house using Lego bricks. The Lego house is not the real house, but it represents the structure. Architects use scale models. Automobile companies use clay prototypes. Aerospace engineers build miniature wind tunnel models. These are physical models. They help us visualize structure and form. The second is a process model. A process model represents a sequence of steps in a system. It focuses on flow, input, transformation, output. For example, think about food delivery. Customer places order, restaurant prepares food, delivery partner picks it up. Customer receives order. That workflow itself is a process model. Businesses use process models to optimize operations. Factories use them to improve efficiency. The third and most important for simulation is the mathematical model. A mathematical model represents real world phenomena using equations, variables, constraints, and formulas. This is abstraction. We take reality and translate it into mathematics. Why mathematics? Because mathematics is the language of nature. Gravity can be written as equations, fluid flow can be written as equations, quantum mechanics can be written as equations. Once reality becomes mathematics, computers can understand it, and once computers understand it, simulation becomes possible. This allows us to analyze behavior without physical experimentation. We can forecast outcomes, we can optimize systems, we can solve problems that are too complex for direct analysis. Now let's answer the main question. How does computer simulation actually work? The process usually has five stages. First, we observe the real system. Suppose we want to simulate a bridge, we collect information, material properties, load conditions, environmental forces, dimensions. We gather real world data. Next, we convert observations into equations, stress equations, force equations, material equations. Now, the bridge exists mathematically, not physically. Equations alone are not enough. We must translate them into computational steps. That means algorithms. Algorithms tell the computer how to solve the equations. This is where programming enters. Languages like Python, C++, Julia, and MATLAB become important. Now the computer starts calculating. This is usually done using numerical methods. Why numerical methods? Because many equations in reality are too complex for exact solutions. Instead of exact answers, we compute approximations fast. Repeatedly, millions of times. This is why simulations need computational power. Finally, we observe the output. Does the bridge collapse? Does airflow become turbulent? Does temperature rise? The simulation gives us behavior. Then we interpret the results. Now let's look at different types of simulation. Live simulation integrates real time data and active participant interaction. This simulation happens while real systems continue operating. Examples exist in engineering, business, and strategic decision making. In engineering, software like ANSYS Discovery helps engineers simulate mechanical behavior in near real time. In business leadership simulations, executives may face a simulated corporate crisis, stock collapse, supply chain failure, public relations disaster. They make decisions under pressure. The simulation evaluates their responses. There is another fascinating idea, the simulation hypothesis. What if our universe itself is a simulation? What if reality is pre rendered computation that deserves an entire separate video? Virtual simulation creates digital environments that imitate real world systems, usually in 3D. This is common in education, professional training, product prototyping, gaming, and virtual reality. Pilots train in flight simulators, medical students practice surgeries virtually, engineers test products before manufacturing. This reduces cost and risk. Constructive simulation combines live and virtual elements. Some participants are real, some entities are simulated. For example, military war simulations, real commanders make decisions, virtual armies execute scenarios. This allows large scale strategic testing. Constructive simulation blends human intelligence with computational environments. Good simulation follows certain principles. The first is abstraction. We simplify reality, not everything matters, only relevant details. The second is accuracy. A simulation must represent reality sufficiently well. Bad assumptions create bad simulations. Garbage in, garbage out. The third is validation. We compare simulation results with real world odd observations. If predictions consistently fail, the model is wrong. The fourth is iteration. Simulation improves through repeated refinement. Observe, model, test. Improve again and again. Now comes the exciting part. How do we simulate nature itself? Take chemical systems, consider rusting. An iron nail slowly reacts with oxygen and moisture. Iron becomes iron oxide, rust. It seems simple, but chemically, thousands of atomic interactions occur. Simulation helps chemists model these reactions. We can predict corrosion rates, we can design anti rust materials, we can improve industrial durability. A simple rusting nail becomes computational chemistry. Now let's go smaller. Atoms. Quantum mechanics governs atomic behavior. Electrons do not behave like tiny planets, they behave probabilistically. That makes physical simulation extremely difficult. Physicists use computational models to simulate atoms. They predict energy levels, bonding behavior, wave functions, quantum interactions. Even modern semiconductor design depends heavily on simulation. Before manufacturing chips, engineers simulate electrons. That is incredible. Your computer exists because simulations help build better hardware. Biology is even more complex. A single amoeba may look simple, but inside it, countless processes happen. Membrane dynamics, energy, metabolism, chemical signaling, biological simulation attempts to recreate life computationally. Researchers simulate cells, protein folding, neural networks, even ecosystems. This helps medicine and biotechnology. Simulation can accelerate discovery, sometimes by years. So, what have we learned? Computer simulation is humanity's attempt to recreate reality inside computation. We begin with observation, we build models, we convert them into mathematics, we run computations, and we predict behavior. Simulation helps us design safer bridges, better medicines, faster aircraft, more efficient chips, even smarter AI. And here is the profound part, every year, simulations become more realistic. As computing power grows, the boundary between reality and simulation becomes thinner. Which leads to a strange question. If we can simulate reality, could reality itself be computation? That question sits at the edge of science, philosophy, and imagination. Maybe one day simulation will not just help us understand reality, it may force us to redefine what reality even means. And that is where science becomes philosophy. If you enjoyed this video, like, share, and subscribe. And